So this is the model of concrete production. This model is done based on the real consulting project we did some time ago. So I'll just run this a bit faster. Okay. The process is the following. The process is the following. Some mix is prepared here. I mean the mix like which will be then placed into those forms, and mix of sand, water, some other ingredients which are needed to produce the concrete. Then this mix is put into these forms and is waiting there until, well, for several hours until it becomes, well, firm. After that, it's taken from here, goes to this autoclave, where it's kept for about 10 hours until, well, like for cooking, let's say. And after that it's ready and it goes to the warehouse. So the initial problem was quite interesting. The guys bought a site where they wanted to build a factory. They ordered the project to the company, got the project, and then built the factory according to this project. And those who designed this factory, they said that the throughput of this factory will be 100 something per day. Let's say. I don't know, I don't remember exact numbers, but remember the percentage. Let's say it will be 100 per day. And then they run this manufacturing process, and the maximum number they could achieve, that was 60% of the throughput they were promised, of the capacity of this manufacturing site they were promised. So they changed the management, they changed the people, so they were thinking the problem not the design, but the people which are working there. So, but the maximum they could achieve, instead of producing 60%, they were producing about 65 or 64, something like that. And finally they said, okay, guys, we have to do something with that. Let's try to do the model. So we did the model and found out that the maximum capacity they could achieve is exactly 64–65%. And the problem was that those who did the design of that, they just used averages to do all the calculations. For example, the mix of this sand and concrete, etc. It have to be in this form for about from 6 to 9 hours, or even 10 hours, depending on the conditions, like the temperature and so on. And so the temperature here, it depends on the temperature outside. It fluctuates during the day a lot. And finally, what we got, that this, oh sorry, I forgot to say that this is the cutting line, when those things just cut it into the pieces. Well, this is very small, very big, like that. And here it's cut it into the smaller pieces, and then already cut it things goes to this autoclave. And finally, it leads to the situation when this cutting line is like a busy 100% or just doing nothing. Just because of these average things here. So, and the most important thing, they didn't have any possibility to extend this line, because they were very limited in the size of site. They just didn't have enough space to build anything else there. And finally, what they did, they just sold the factory. So
the factory came up with the idea to model this? I mean, who came to you and asked you to model this? Because it's probably, I would think, this is not the first approach that they will take.
Yeah, first they were trying to change management. Just trying to find a solution this way. But then one of those guys who was the owner of this factory, they visited one of our seminars and decided to do this model. Because, well, he was really disappointed. So he was saying, okay, that's the calculations, I'm sure this company, well, that factory was built in the 90s. This factory was in Russia, the design was done, I'm sorry to say that, by German company. So, and they were pretty sure it should work well. I don't know why it happens, why the design was done in this way, and but well, that happens, and why they decided to, well, again, they were almost 100% sure that they can reach this capacity. But once they realized they can't, and also it was very visual, well, the model actually reproduced in very details the real situation on the factory, and they completely trusted. Another one of that. This is.
Sorry, so that was discrete modeling, wasn't it?
The previous one.
Yes.
That's mostly discrete, but there are some agent-based elements there, because it's not. Some elements on this model describe very good with the process, but some of them, in particular those forms, as I remember, well, it was more difficult to model with discrete event than agents, so it's a kind of mixed model, but agent part is very, very small there.
Mm-hmm. And weren't you asked to find out where the bottleneck is? Because that's what I would want you to do. To find the bottleneck, why this is not working.
Say again, sorry.
I mean, in the whole process, I would request you to find out why this is not working. Where is the bottleneck of the whole process? Weren't you asked this? And didn't you try to find out what needs to be changed?
Yeah, that was the purpose. So I mean, they wanted us to find the bottleneck, and well, no, that's the original problem definition was like I already said. We assumed it has to, it has this capacity, but the capacity we were able to achieve is much less. So we are interested what's going wrong and why we can't reach this capacity. What's the problem? People, maybe they're just slow with some operations, whatever. Yeah, finally that's actually the problem of finding bottlenecks there. But it's but you see, bottlenecks, sometimes it's quite easy to identify, right? Even without simulation modeling. But for them it was not obvious why it happens. You see that, for example, they're saying, okay, maybe that's not the problem of these averages, but the problem of people. That people just does not do something in time. Let's say instead of spending like 1 minute for operation, maybe they spend 5, and that's the reason why we have these, well, bottlenecks here, here, and here. And also there were several bottlenecks, like the cutting line, then autoclave, and so on, because one bottlenecks also produce other bottlenecks in the system. And they were thinking, okay, maybe we are lack of autoclave, and we have to just increase that, and then everything will be okay, even in spite of this, well, even without taking into account those averages, just increase the autoclave, and then everything will be fine. So basically, they could see that there are some bottlenecks in the process, but they could not understand the reason of this bottleneck. Does it make sense to you?
I have also one question. It seems like it's pretty real system, in the model. So you also had to create all the transportation algorithm, right?
in this model, we mostly use, yeah, you basically, the question is right. So in this model, we model this transportation with the timings. I mean, we just measured the real time, let's say, to transfer some details from one point to another one, and just use these timings. We didn't implement the algorithms in this particular model. We just use timings. Move from point A to point B, let's say. But on the next slides, when I'll be talking about atom, I'll talk about those algorithms to optimize transport operations. Green department. This is the entrance of bills, let's say. The bills are generated here. We have two types of bills, like the contract bill and, let's say, standard bill. We may manage their rates just by moving this slider. Oh, yeah, sorry. Yeah, depending on the type of the bill, there is a different process of processing this bill. And also there is some stochastic there in terms of that occasionally the clerics should check the bills. That's the problem, that somewhere the line for this one isn't, the capacity of this line isn't enough. That's why we got this message. That's because of I changed the arrival rate of the bills. So, yeah, by the way, we may just drag. Oh, it's very fast. Okay. So you may track particular bills, just see how they are going through the process. You may measure the time which is spending to process normal bills and contact bills. Also, you may manage the resources. Let's say you may just in the runtime mode, without changing the model itself, you may just increase the number of resourcing. Let's say saying now we have not 3 but 5 people. We have not just one but more printers, and see how those resources will influence the process. We may increase the rates and again see what will happen. We may observe the utilization of those resources also, and make some do some what if experiments. You see this slide that is increasing. So now we need to this reduction. So this is poor discrete event model. Pedestrian model. I already told you a bit about that. So in this kind of modeling, each person, each agent here, this agent may observe some distance ahead of him or her. It can see the physical space, the walls, escalators, elevators, and so on. So you can see some service points. So the purpose of this kind of simulation models to model the physical space and how the agents or people will behave in this space. In order you could plan this space in some way. I do not want to say optimal, because optimal is not always possible to find out, but at least you may try various scenarios, how to locate things inside some layout, where to put some shops, some service points, I don't know, how many passport controls we should have, how to organize the space before the passport control at airports, for example. So that's the that's what can be done with this kind of modeling. Let's switch to the animation. So this is a density map, and here we see that probably we have to do something here, because the density map here says that there is a quite significant density of the people here. We have to think how to avoid this, those situations. Maybe we may just close this exit, or maybe we may just put a separate line here, in order that those people would not interfere with those who just come out of these facilities. By the way, this is a real subway station in Marseille. Yeah.
How do the pedestrians find their ways?
They find the ways themselves, depending, well, they see the pedestrians in front of them, they see the walls, they have like a destination point. Let's say those who enter here, they may go here, but the way inside this environment, they choose themselves, depending on the density of the pedestrians, depending on the walls, and so on.
But you also have a routing algorithm up front. I mean, no pedestrian is running into the rooms.
Into the rooms, you mean? Those?
Yeah.
No, it
for
just
example.
didn't. It wasn't taken into account, because that's not the rooms for pedestrians. This is the rooms for staff. I mean, like police, whatever.
Are the routes,
More questions about that?
are the routes fixed? So do you determine from
Oh yeah, sorry.
do you determine right from the start where to, which agent, which passenger to go from where to where? Can you model something like okay, a counter is closed, so I have to switch my route? Or,
Yes, you may change destination point in dynamically.
dynamically, so I can combine a pedestrian simulation with a discrete event simulation, and if one event occurs, I can change the destination for the passengers.
Yeah, that's a very good question. So, first, pedestrian models can be combined with discrete events because of that there can be different reasons. First, it can be some logic, which is easy to describe with a discrete event approach. Second, the pedestrian models, they're very resources consuming. There are a lot of calculations are done on every step. And if you, let's say, try to do the pedestrian model of the Berlin, well, probably you will have to have a supercomputer, let's say supercomputer. Those pedestrian models is often used exactly to model some, I don't want to say bottlenecks, but say the areas where there is a potential congestion problems. And do not model with this pedestrian approach or pedestrians the areas where there is no any issue. Let's say if you have like 100-meter hall and just one pedestrian there, probably there is no any sense to consider this hall, to model this hall with that much details. But if you are talking about passport control, yeah, it makes sense to do, right? So, pedestrians, they may change their destination point, not only with the discrete event, but just remember the pedestrians themselves. Inside the pedestrians, there is a destination point, and you may change this point if something acute. But we do not. But if you try to reproduce the real behavior, usually the real behavior is following. Yes, so you may just hear something that was announced in the area, and in this case you may change the direction. But also you may just find out that something is closed and then go another way. See?
Okay. Okay.
So yeah. But the destination point can be changed.
Internal and external events to a
Yes,
destination.
yes. So
Okay.
this is the pedestrian is an agent in terms of AnyLogic, and as an agent you may just send there some events as well as pedestrians may generate events too.
Is that density map, is that automatically changed during the run, or is that
correct.
based on historic runs and then put on?
No, it's changing during the
Okay.
during the time. It's calculated within some time window. For example, if the pedestrian density will be decreasing in this top right corner, then the density map will be changed too. It's calculated not from the beginning, but during the some time window. Does it make sense? I'll just demonstrate one more model and we'll go from it, okay? Two stocks problems, that's about logistics. This is a simple, well, from the simulation point of view, this is quite simple model, but I think the problem definition was interesting. So there are two cases here, right? There is a, let's say, distribution center here, and the goods are delivered to West Virginia. And in another case, when we have a distribution center here, all the goods directly from the port delivered to this distribution center, then from the distribution center delivered by lorries, not by trucks, to the end customers. So the idea of this simulation, the original, was the following. The company was trying to, well, they decided to go to North America to sell their products. And they solely were thinking about the infrastructure they have to build there, but also they would like to plan their investments, how the business is developing. I mean, with the business development. I mean, they would not like to invest a lot, let's say, into this solution and then found out that they do not sell enough to make this solution reasonable. So. And they were trying to find the time, at what time they have to build a distribution center here, and at what time this scheme will be more efficient for them than the first one when they deliver everything from the port. So they have some.
The break-even point can be read out of the.
From the data, yeah.
Okay. So the analysis has to be made afterwards.
Yes, and also in the real model, there were a set of controls which they could manage during the simulation. Let's say that they work for some months, then they change something and see how it works further. So they were interested also just in this what-if analysis, how the system will react to some changes in this, let's say, in this environment.
So can you estimate how much time it would take to set up this model and the graphical stuff and so on?
Oh, this one, that was very easy. All the things, collecting the data and so on, that took about 5 days. So I mean, collecting data, developing the model, providing the results to the customer, and also customer agrees to that we put this model into the distribution set. I mean, simplified one, but.
Short question concerning the data. Doesn't concern this model, but models which are more complex. Is there any way to read out the data to do statistical analysis?
I'll show you that.
Thanks.
Yeah.